hopefully, whoa, that feels very loud. Hopefully everyone is in the right place. I'm here to talk about embedded C and C+ development in the cloud. My name is Jonah Graham. I work for Kitra Coders. I am Kitra Coders. I'm an open source advocate. I've been doing open source software for a long time. I've been involved in the Eclipse community for feels like forever. Got to stand up one of the first people in that earlier talk. So, but a lot of my focus has been on C and C++ development tools. I'm a project lead of various Eclipse projects and committer, and I've come to talk at EclipseCon today about a couple of topics related to C and C++ development. So let's jump right in, and let me tell you about zero install and how it applies to embedded C and C++. So what is zero install? And how does it apply to development environment? You know, the main thing is we get away from setup. We want things to just work. We don't want any more of this. It works on my machine things and it doesn't work on other people's machines. So, you know, we see lots of examples of this these days, but you know, we want instant access. We want things to be cross-platform. We don't want to worry about what other people have on their computers. We want it to just work. For embedded C and C++, it doesn't really change that much compared to if you want to do Java or TypeScript or anything else, until you get to debugging and actually running code, because you know you're not running on the same computer. You want to run on this real piece of hardware that's sitting next to you on the desk. Real hardware tends to use JTAG or other things, but let's use JTAG for today. So for us, zero install is going to mean getting this cloud type development environment to work with WebUSB as the way to connect. So I'm going to take a bit of an indulgence here, and I'm going to go through the design progression. So I've spent a few weeks here and a few weeks there over the last many years looking at the evolution of this space of running in the cloud. And before we get to step one in this area, you know, step 0 is the traditional ID. You download Eclipse, use Eclipse CDT. You might use VSCode or something else these days, not Eclipse, I don't know. You install all the tools on your own computer. If you're lucky and your supplier has a nice installer, maybe you can install all of them in one package. Otherwise, you might be going all over the place, pick up your GDB here, your J-Link there, and try and get everything to work together. So, nice and simple. All your software is on your one laptop. Plug in your development board to the laptop, and you're good to go. So, you know, some of the main pros for it, we already have it, right? Like if you're a company, you're trying to decide how to deploy an IDE. Well, Eclipse CDT already works. You don't need to get anything new. It's relatively secure. You're not exposing yourself any more than your own computer might already be exposed to the world. And when you're putting these different tools together, you know, if you're writing a new tool, you can write that tool in the language that suits it best. So it gives a lot of control to the user, which is also one of the big cons. Obviously, it's the opposite of zero install. You're installing everything. But that maximum control for the user means that there's so many more things to assemble on. You know, getting drivers to work on Windows, just getting anything to work on Windows. User end up having to manage all of that. And if you jump on almost any embedded forum, there's just tons of questions on different versions of different software and how do I get them to work together and all interact together. So that's what we want to try to get away from, that con. So, step 1. Step 1 is no WebUSB. We're just going to debug entirely with the cloud. We're going to take the IDE, you know, Eclipse IDE, VSCode, whatever. We're going to split it in two. We're going to put the graphics up in a web browser, but then everything else we're going to leave running back in the back end. All that logic, all of the connecting to hardware, the single-step logic, all that just runs in the cloud. Then the board has to connect to the cloud, and it can do that through secured connections, unsecured connections. You know your developers. What do you think they're going to do? So, simply said, we're going to take out all of these bits that were down here on the computer, just move them up there, and now all we have is the web browser down in the down on your own computer. But the development board now is not connected to your computer. It might be sitting next to you on a desk, but as far as the GDB, it's really far away from GDB. So I'm going to, I did this project a long time ago. So it's using Che, and it connects to a board to demonstrate this. And so what we're doing is we're doing the debug. So we do a debug, and what it's just doing is it's copying. I don't know if you can see that there, but it's copying the executable to the board, and then it's just running GDB server on the board and exposing the RSP port, for everything to go. Start up the debug session, and that GDB has just done, target remote, the IP address, and that 1234, and now it's connected to it. And then we can single step. As you can see, the single step performance here looks okay, but that's because everything's actually running on my computer. It's not really, I don't actually have the cloud side running on a off-site somewhere, 1,000 miles away. So as soon as you do that, the single step performance becomes really bad. So in this option, and this option is deployed, there's a number of cases that do this today. They might have the board on your desk. They might have the board close to the cloud farm, which makes debugging a little bit easier. But the big advantages of this is you can just take your entire debug stack. You don't have to write anything. It just, it just works. It's going to be the same code that you're running for the desktop IDE that you've been testing for 20 years. So if you're trying to get something up quickly, this is great. You just switch over to this immediately. Now, the cons list, the text got really small for the cons, didn't it? It's because of a lot of things. Kind of one of the big problems is that you need a big board in this case. You need a board, maybe running Linux even, so that you can run GDB server on it. It's not terribly great if the thing you're actually trying to debug was a remote control, which might have a $1 CPU on it. You don't have to have a big board. There's other ways you can have big other pieces. You can have other types of proxying things so that you do it. But you are requiring something extra to make this connection in a way that is more than just a simple USB connection. If you have a cloud computer connecting to the board on your desk, that means you're exposing the board on your desk to the internet. Now, you can do it. You can set up security. If you saw my video, we SSH'd the executable down to the board, so that's nice and secure. But then the very next thing we did was start GDB server and expose RSP on the internet. So not secure, but that's really easy. It doesn't take much effort to do that. You want to put an SSH tunnel in there, then you got a whole extra set at every level that's going to affect and complicate your life. And it can be very slow. So if that board's on my desk in Ottawa and the cloud servers in Germany, every single step is going to require many round trips. A single click of step instruction, it might only require a couple round trips on the UE side, but every layer down the protocol, it's going to be more and more steps to complete that. And it might be dozens. It might be dozens of back and forth round trips, and at the 10, 20, 30 milliseconds per round trip, we're starting to be a very noticeable bad experience for the user, let alone if you want to start looking at all the variables and everything else. So all those steps, all that interaction is not really a big problem if you're doing local debug. You're not going to notice over USB a big slowdown these days. If you want to do, like I sort of mentioned, if you want to do the secure version or not big board version, there's a bunch of extra setup steps compared to your local development environment. So let's see if we can improve this a little bit. So rather than installing all of the debug stuff on the cloud, let's just install just the debug stuff on the local computer. So we're going to run all the editor, all of the file management. That's going to look just like how normal Theia or VSCode in the web would look. And then we'll use a WebSocket is a traditional way to get out from the web browser into your local machine. And so we'll have the web browser use a WebSocket to connect to our controller. And then that controller software will bootstrap up all the launches. It'll launch a debug adapter. The debug adapter will then go off and launch GDB and GDB server, and everything will work great. The controller doesn't have to be a piece of software. Your users would probably rather it was a piece of software. It can just be tell your users to do this. So what this looks like is now we've moved all of these programs, the debug adapter, GDB, GDB server, that was in the cloud, and we've moved them all down here as local programs onto your computer. And it says DAP here's like if you're running the VSCode's debug protocol, DAP wrapped up in a WebSocket as the communication method, and then the controller over here will untangle the WebSocket and convert it to something that the debug adapter understands. So there's some really good pros of this. One is your debug stack is shared with your traditional IDE, your local IDE. It basically solves all the performance problems that you had before. All your single stepping is now local again, so everything works great. And it also solves a lot of the security issues that we saw. Now we're not exposing anywhere near as much to the internet. We are exposing still to localhost, and there are some real security considerations on that. If you're opening a WebSocket server on a user's machine, there needs hire someone who knows what they're doing. I think I say that in the next slide. But so we are back to not being anywhere near zero install. We're a lot less install, but here's an example of just some of the programs you might need. You'll need Node, you'll need the debug adapter, maybe some proxying tool or a controller, the GDB server, the JLink driver, so not zero. It's pretty complicated to run this manually. It's doable, but I wouldn't want to tell your users to start WebSockify, ideally. So you want to invest in a custom controller, and I have a little demo of one that we did. Just leave some screenshots. There are still some security considerations left. So, if you guys are deploying a program that's opening a WebSocket on a user's machine, hire someone who understands web security and make sure you do that right, because otherwise you are going to have a security problem down the road, especially exposing something as powerful as a GDB server type thing on a WebSocket gives full access to your computer. There's another change that needs to make. While you can reuse much of your software, somewhere within this stack, you're going to have to actually get from the web browser to the local code. And so, a VSCode web extension will work. Although I think the first iteration we did on this, we just hacked the source to get it to work. We didn't have web extensions yet. So yeah, this is some screenshots sort of version. I didn't have a good web recording for this one, video recording rather. So we wrote a little program we called USB debug. USB debug, I think it was mostly an opportunity for me to learn Go, so it did have that advantage. But it opens a WebSocket up, and it would receive an instruction from the extension running, and that would start the debug adapter. But once the debug adapter started, then after that, the flow is entirely normal. So as you can see, we have the JLink is running here. So USB debug, eventually JLink will get started. So when the user chooses to run a debug session, then the USB debug says, hey, a new connection's coming here, which is in the allowed list, so it's going to proceed along that way. So let's see if we can do it with a little bit less installing. So the next few steps are some incremental steps. Let's just move some stuff a little bit into it. We're not going to get to zero install, but the less stuff we put on the user's machine, the easier our life is going to be. So easy first step, move the debug adapter from your local program into the web browser. And that's great because JavaScript's come to our rescue here, because it's in JavaScript already, or hopefully TypeScript, something like that. For years, I swore I'd never become a JavaScript developer, and I'm still trying not to be a JavaScript developer, but I'm definitely in the JavaScript ecosystem these days, as so many of us are. And I haven't read the full definitive guide because it looks not worth it. That says the good parts on the left, the little one. So we moved the debugging adapter to the browser. It's easy. It was already written essentially in JavaScript. We have to update how some of the launch mode works, and the VSCode API eventually came along and added in inline launches for debug. So that meant we weren't having to actually modify anything in VSCode side to just get this to launch. A little tip if you're doing this, you try and move your debug adapter. Debug adapters generally, if you follow like the initial how they're written, they run as their own process. So every time it gets launched, you have all your state cleared. It makes your life easy. Once you move it into the web browser, you're not going to have your state cleared. Your state is going to be maintained through different debug sessions. So make sure you don't have any unexpected globals in your code. So the next step, and sort of the one that is quite interesting, I think, is move GDB up into the web browser. GDB is not written in JavaScript, so not as easy, but WebAssembly works in these days. And so using mscriptn meant I didn't actually have to rewrite GDB in JavaScript. So for those who don't know, WebAssembly or WASM is a binary instruction format for stack-based virtual machine. So we can now take just your normal C and C+ code, or kind of most any other language these days. It can be compiled down to WASM as the binary format, and then that can run in the web browser along with JavaScript. Using mscriptn, we were able to convert. You can convert a program to a web browser, but it's not quite as easy as just compile it and done, because it doesn't really work the same. So relatively easy. You can compile it. If you go clone GDB, get mscriptn, hit compile, then you're going to get a gdb.js file right away, which sort of works almost, until you want to interface to the external world a little bit better. So kind of two main places GDB needs to interact. GDB needs to talk to the user or to the debug adapter. Normally it does that on standard in and standard out, talking MI, and it needs to talk to GDB server with RSP. So we needed to improve that lower level to make that work. So first talk about connecting to GDB server. Now RSP is just a serial protocol. All we need is an input and output stream back and forth. So when we just moved GDB in, what we did is we said, okay, well, the way to get outside the web browser is WebSockets. So we added into GDB a different target remote. So I don't know if you know the internals of GDB, but if you target remote in GDB, then it starts parsing the beginning of that to see, to understand which one of the handlers to pass that to. So we added a new handler for ws://. So if you do target remote ws://, then GDB will create a WebSocket and connect to whatever that is. And at the other end, you can use WebSockify to turn that back into normal TCP/IP and connect to GDB server. Or you can implement GDB server can implement the WebSocket directly if you like. And then for standard in and out, we created, a concept of a buffer. The basic mscriptn implementation, it's very POSIX-like down to a layer, and then all of a sudden it becomes very JavaScript-like, and the JavaScript-like is like, okay, well, I can just create heaps of memory, and every time I do a write, I'm just going to take a string and pass it off to the console or something like that. But we needed a slightly better system to control that flow, identify when data is available on the input, which is actually the part that's less well implemented. The output from mscriptn by default works pretty well. The input needs some more work. So we create a buffer. It allows us to do reads and writes without delay on GDB side, so we're not having to wait unless the buffer is full. And then we use atomics with shared array buffers to actually achieve that pausing of the process. It allows us to pull critically allows us to pull the input to find out whether there's available data, so it knows what to process. Because what GDB has to do is it has to talk to two ends. It has to talk to the GDB server and the GDB adapter, and says, okay, well, who has instructions for me? And the naive way of doing it, where you just go read one while it's a blocking read, then you never find out that you have something coming from the other side. So we implement a complete buffer to solve that. So one of my favorite little demos, so that's GDB up there, is running in a web browser. You see it's just normal GDB. I did help up there. I did print 4+5. This happens to be GDB version 7.11. For some reasons, it was simpler to just get that as the first working version. And here I do a target remote, and I pass it localhost 2345, which over here you can see is my WebSockify. It's going from 2345, passing it to the standard J-Link. Port number is running over here. We've got J-Link running over here as a GDB server. And every time I continue up here, you can see a whole bunch of WebSocket packets. And every other time I press continue, that light should turn on. So there's the LED turning on and off because Blinky is running on that board. It's just going to restart. But that's the first full running of GDB in WebAssembly. But, as you expect, there's still a bunch of software that's running. There's still a bunch of software that's running locally, so we're not yet at zero install. So, step 3, actually zero install. The last piece of this puzzle is WebUSB. So, we move more and more into the browser over this time. The last step is get our actual hardware connection. WebUSB is sort of a bit of a natural one. It's a very common way to connect. There's also Web Serial. There's an interesting case with file system APIs, especially if we're only talking about the flashing part. A number of boards will expose itself as a mass storage device, and then you can program it. I don't know if anyone has ever then tried to make special files in that mass storage to allow a debug communication. It's an interesting concept that we've never really expanded on. At this point, this is when we're moving GDB server into the browser as well. Most of this has been working with Renesys' stack, and Renesys GDB server uses J-Link as a library, so it's just one executable, so they're very tightly coupled, so that they got to be moved at the same time. But GDB server is written in C or C++, so it's going to use the same WebAssembly compile toolchain. So, we got rid of that big blue box that said local install. We are now at a real zero install web browser with everything running in it, connected to a development board, in this case J-Link, using WebUSB. Now, once we get to WebUSB, we sort of touched on it a little bit before about the buffers, but once you get to WebUSB, the difference in programming models of your traditional C program versus your traditional JavaScript program really comes up, and that's synchronous versus asynchronous programming. Everything in JavaScript, it's all promises and events and things like that, whereas in C you just call and block and stuff and use methods like pull and select in the standard library to find out if something is ready to happen. So the model that we decided to go with is to run GDB in its own web worker, and that way, and GDB server in a separate own web worker. That way, each one of those processes each one of those web workers is kind of equivalent to a process you used to have on your computer. And then, when you have to do any kernel type operations, you want to talk to the standard library, that gets handled by a different web worker. And they communicate with each other using atomics and shared array buffers. So this way, we can pause the WebAssembly. And there's other ways to achieve this pause, but this is, based on our development timeline, this is what worked best for us, or is working best for us now. So what it does is it allows you to take like the WebUSB APIs, which is transfer in, which returns a promise that you then have to go and handle, or transfer out, and converts them to so they can just be used synchronously. We took that buffer from before, the WebUSB driver, and made a package called WebKernel that we're using. It's got sort of three main parts. It's got the I/O buffers, which handles all the streaming interfaces. So we have, in our model, we have one that connects the debug adapter to GDB, and a whole other one, another instance of the same set of classes that connects GDB to GDB server for the RSP protocol. Then we have an RPC model. So the buffers allow for continuous flow of data, whereas using an RPC type model means from the C code, it makes a function call. That function call has to complete before it returns. And so we use RPC to handle the WebUSB. We use the RPC to handle file system. So GDB, GDB server, both want to access the file system, the ELF file that GDB wants to read all the symbols from. So we'll use an RPC server that's running in the kernel side to make calls, and it uses shared array buffers to do that with atomics. And the last main component is just all the launching, so that you can launch these programs, set up the current working directories, mount the workspace file system, pass command line arguments, so that to the debug adapter or to each other, everything looks as close to a traditional process launching that you might be used to. So we're at zero install. Having all this working means we have a good user first experience. It simplifies our testing a lot. We're now not really dependent on the user's computer. We're only down to the user's browser. Almost all the security issues that we have of exposing this, that, and the other thing are all resolved because we're going to rely on the web browser security model for WebUSB rather than having to come up with our own implementation. So on the con side for zero install, we need a version of all the code that runs on the web browser. So we have to rewrite things. We have to use WASM. We no longer use the same GDB executable on the web zero install version as we do in any of the other cases. We do need browser support. So I said, just use WebUSB. At the moment, WebUSB is only supported by Chromium. At the moment, Firefox's statement is they are concerned by the security implications of WebUSB, so aren't even planning to enable it. Maybe that will change one day. A risk of this is that browser evolution is pretty fast. Things do keep changing, and so you do have to retest your stack, with every new version of Chrome that comes out, and or keep track of what's coming. So for example, as the shared array buffers at one point got disabled by everything because of security considerations, and then when they got re-enabled, you had to send specified headers and make sure all your sources came from the same place, or I don't know, there's magic headers that had to come in there. I don't know all the details. It is write once, run everywhere, but you also have to test it everywhere. It's not going to work unless you test it. And the last thing is we're really at the mercy of this browser ecosystem, right? At any point, the Chrome security team can just decide, actually, you know what, WebUSB, there's just too many security risks, and we're going to disable it for a new class. There's a bunch of classes of USB that aren't supported for WebUSB, and it would really suck, but they can come along and say, well, actually, JLink looks like a class of WebUSB we don't want to support because it's too much of a security vulnerability. So I have a little demo of what this looks like. So we have our test web extension here. So it's just sort of looks like the normal debug adapter web extension. I have a simple project here that generated before. It's just normal code, nothing special for that. It's just compiled for that board. So you can see, it's just, and then in the debug launch, it looks sort of the same as a normal launch. one of the key things, all your ELF files are listed there, and one of the main things is that we just have a new debugger type. We say we're a WebUSB JLink, and connect to each other with dev RSP. All of the command line options you might need to pass to your GDB server to set up all the memory regions and specialness all exists. And when you hit launch, you get prompted by the web browser about which JLink to connect to, and then you press connect. And then after a little delay here, for this video recording, I used the full debug version of GDB server. So the first load is a little bit slower. It's about 15 times bigger executable than it is when it's fully optimized. And after a little bit, GDB server's up and running, and we're connecting to the board. And then after that, GDB will start and download and everything. So, in conclusion, the main thing is that zero install is actually possible for embedded tools. It's not limited to all of the Javas and JavaScripts of the world. Using WASM, mscriptn, and all web extensions, these are all just enabling technologies to make this happen. But the ecosystem is evolving quickly, and that makes it a challenge to be involved in. We're not, Eclipse IDE hasn't changed as quickly as this, so this is a much faster evolving place. But that's obviously a big opportunity, while everything is changing. So that's my presentation on zero install. I hope you learned something new about it, and excited to run to your computer and figure out how to get it working for your own products. Is there any questions on this?
Two questions, actually.
Okay.
First one about JLink library. You say it is linked. You also recompile it to WASM or JavaScript, or how it was done?
So the JLink library itself is a rewrite. We're not recompiling the JLink DLL because that's Sager's own source code. So we're having to rewrite it.
It's C++ and mscripting.
No, actually, I think the JLink library is entirely done in JavaScript. So we have it entirely done in JavaScript library. I believe part of it is provided by Sager, and most of it's provided by Renesys, being written by Renesys. And it's a work in progress. So.
Yeah, and speaking about WebUSB interface, are there anything in WASI standard interface to USB? Because then it could be enabler.
I don't know if WASI has any USB implementations in it. I have a whole bunch of, I have other slides about WASI and about all the other different technologies and ways to connect it. But I don't know if actually WASI has a USB listed interface. So, yeah.
Let's hope it will. Yeah. Thanks.
All right. No other hands. So I'll say thanks for coming, and look forward to seeing you the rest of the conference. Come grab me if you have any questions.